This is a video presentation for our APSC 459 project, DROPS, the Drop-Off Recognition Optical Processing System. The main focus of the project was being able to detect drop-offs, calculate the expected depth and distance away from the user, and warn the user immediately. Examples of drop-offs include drops in height seen at sidewalk curbs, stairs, and SkyTrain platforms. This project was sponsored by Dr. Cyril Leung of UBC's Electrical and Computer Engineering Department.
I'm Pranav Saxena.
And I'm Rosanna Yi.
We wanted to develop an electronic device to aid the visually impaired in navigating their surroundings. A representative from the Canadian National Institute for the Blind, the CNIB, suggested that drop-offs were potentially a significant challenge, especially for those with walkers or wheelchairs, as they might not know about sudden drops until they are too close to the edge. Further research showed that no commercial product for the visually impaired was currently available for detecting drop-offs. Our goal is to prove the feasibility of a system aiding in such a task.
In order to do this, we have used Visual Studio C++ along with OpenCV, a popular open-source computer vision library. We also used the Minoru 3D webcam, which actually consists of two separate cameras, giving us a stereoscopic view of the surroundings. On the right is a demonstration of our setup for a potential user. The Minoru is in a vertical configuration, as this allows us to more easily recognize horizontal drop-offs.
How the system works can be summarized in a few steps. Edge detection, simplifying images into their edges. Edge location, finding the edges that are significant. Stereo vision, using two cameras that are aligned, calculating the disparity between the two images and hence the perceived depth. The calculations and image processing has to occur quickly so that video feed processing can occur. And lastly, oral feedback is given to warn the user. Please note that with every loop, two images are processed and analyzed, one from each eye of the Minoru camera.
Because drop-offs are characterized by edges, by simplifying the camera input and reducing it to edges, unimportant aspects of the input are filtered out and the overall processing time is lowered. After researching different algorithms, a hybrid of the Canny and Sobel edge detection algorithms were chosen. Firstly, the camera input is smoothed to reduce noise, and then the magnitude of the overall gradient is calculated. Where there's a large gradient, there's likely an edge.
After performing edge detection, it is necessary to highlight important edges for the depth calculation. This edge location algorithm scans the edge detected image for continuous edges of various angles and curvatures, predominantly in the horizontal orientation. Now, in order to simplify the process further, edges intersecting the center lengthwise line are identified and chosen for depth analysis. Once these chosen edges are obtained for both camera images, they are matched according to the order in which they strike the center, from the bottom up. This matching allows the software to identify the same edge in both cameras.
With the edges matched, it is now possible to calculate the real-world distance to each edge by using the disparity between two matched edges, or the difference in pixel distance. By using similar triangles and geometry, we can solve for the straight line distance to the edge in question, z in this case, and the shift in the perpendicular axis, x in this case.
However, due to the Minoru cameras having a narrow field of vision, it is necessary to tilt the cameras. We have tilted it approximately 42 degrees. This allows us to detect drop-offs at closer distances, but also comes at a cost of more complex calculations. As shown above, x is now y prime, and z is now z prime. By utilizing our tilt angle, we can calculate the depth/height of the edge in question, relative to the bottom camera. By running this calculation on successive edges, we can find the height difference between them, the depth. For each frame, 5 sets of successive edges are checked.
It was also necessary to test and rate our system. The general parameters used were the location, the distance from the edge of the drop-off, and the angles the user was oriented at relative to the drop-off. Data was collected as a continuous feed for 250 frames for a stationary user. Data collected includes calculated drop-off heights for all edges, and for the first two successive edges, the calculated range from the user to the drop-off, and the average frames per second of the feed.
Here we see a graph displaying our calculated depths and measured depths for all detected edges. The calculated values are close to the actual values within an average error of 4.22 centimeters. However, we did observe a high coefficient of variation, 48.8%. This graph is very similar to the last, except that only the very first two edges were considered for measurements. On average, this resulted in a better error, 3.33 centimeters. The coefficient of variation was very similar, 49.2%.
In review, our depth calculations were reasonably accurate and meets our error margin of 3 inches, though the coefficient of variation was much higher than expected. The average processing speed was 6 frames per second, which is 1/5 of the Minoru sampling speed. In our testing, we found that the Minoru camera was not designed for outdoor use in very bright conditions, as the lighting can overwhelm the input and make it difficult to perform analysis. It was also required for a street curb to have an edge on the road, so there is an edge to compare with the edge of the curb, as seen in the picture above. We also had issues with calculating the distance between the user and the drop-off, but are currently working to fix this issue.
After testing, we were able to define the physical limitations of our system. It is able to detect a drop-off anywhere in between 0.4 meters and 3 meters from the user. It is able to detect drop-offs at angles between -30 and 30 degrees relative to the horizontal. In low light conditions, there is a slower response time and it is unable to operate in darkness. And lastly, in the presence of intense light, input is washed out and unable to be processed.
There are various improvements that can be made to the current system. Currently, oral feedback is not implemented, but we hope to complete this soon. Outdoor performance could be improved by adding an IR filter to the Minoru camera and will be completed and tested in the near future. Calculations for range are inaccurate, possibly due to correlation errors from noisy drop-offs. The fixture holding the Minoru could be redesigned to be more user-friendly. Optimization of the algorithms could also improve processing speeds.
Now we would like to show you a video demonstrating the use of our system. Here is a video showing you what the system sees. And lastly, the output for a hypothetical user at the SkyTrain, albeit without sound.
That was our presentation for our APSC 459 project DROPS, the Drop-Off Recognition Optical Processing System.
Thank you for your time.